question 21, we just have to find the products of these three reactions. So the top two, this is the old chestnut about the relative acidity of a carboxylic acid and a phenol. Okay, and what you hopefully know is that the carboxylic acid is much more acidic than the phenol, so while they both react with a strong base, like sodium hydroxide, only the carboxylic acid will react with a weak base, like carbonate. And that's a story you absolutely have to know, and this again is the evidence that this is a sort of favourite of theirs. So with sodium hydroxide, you've got to recognise that both of these groups will form salts. So you've got the core of the molecule is still the same, but the COOH becomes COO minus Na plus, and the OH also becomes the salt, so O minus Na plus, like that. With carbonate, only the carboxylic acid does it, so it does the same thing, but the phenol stays unaffected. So we'll get salt of the carboxylic acid, but the much weaker acid, the phenol, can't do that with carbonate, so it just stays unaffected. Now the one at the bottom is electrophilic substitution with bromine. So remember that OH, a phenol group, activates the ring, which means that it can react without a halogen carrier catalyst. If it was a benzene ring without an OH, the answer would be no reaction, because the low electron density means it doesn't react. But once you have an OH there, it activates the ring, and it activates it at the 2, 4 and 6 positions. So 4 is blocked, so it's going to go to 2 and 6, which are at those positions. It may not react at both of them because it depends on what the effect of the other group is, and they would let you get away with just putting it at one of those positions, but you may as well keep it simple and just remember that 2, 4 and 6 are the activated positions, and any of those that are free we can just do the bromine substitution there. So we get bromine here and bromine here, and that's it. In part B we have to work out how to take this compound, turn it into an acyl chloride and then into a polymer. So you just have to know that the reagent that turns carboxylic acids into acyl chlorides is SOCl2, which is called thionyl chloride, but the thing you really need to know is the formula. So as so often with organic chemistry, you just have to know that. There's no way you're going to be able to make that up. So that will give you the acid chloride, and all that happens is that COOH becomes COCl, so it's a very simple transformation. That's the acyl chloride derivative of the carboxylic acid. And once you've got that, two of these molecules can join together, because the acyl chloride group on one can react with the phenol group on the next to make an ester linkage, and obviously that process can then continue and build up a polymer. So you just have to remember how to construct the repeat units of the polymer, and the thing to remember is just that the OH group, when an ester is formed, just becomes oxygen with a linker bond, and the carboxylic acid group, or in this case acyl chloride group, just becomes a carbonyl with a linker bond and loses the chloride in this case. So your repeat unit just looks like this. O benzene ring, make sure you get the substituents in the right place, so at 1, 4 position, and that will give you CO. And it asked for 2 repeat units, so it just does the same again. So we have another oxygen, and then we just repeat exactly the same thing. CO and the linker bond. So we've got the same repeat unit twice, and then we just draw a bracket through the linker bonds at the end just to make it clear that that's what they are, linker bonds like that. And you can always check that you haven't messed up the ends. The common mistake is to like put an extra oxygen in or leave an oxygen out or whatever. So you can tell if it makes sense, because if you then just, in pencil or in your head or something, start saying, right, what will the next repeat unit look like? Well, it's going to look like that because that's the beginning of the repeat unit, so it's going to look like this. And as soon as you've drawn that, you realise, yeah, that looks right because we've just got another ester link in the middle. So always do that test just to make sure that you've got the beginning and the end compatible. Okay, so then you can just get rid of that and say, right, that's my answer. C, we're asked to work out the concentration of M, this component, in moles per dm cubed, given that we know the concentration of K, which is this component, but we know that in grams per dm cubed. So the thing to realise is that the intensities of these peaks in a gas chromatograph are proportional to the concentration in moles per dm cubed. Okay, not in grams per dm cubed. So the first job is that we've got to convert grams per dm cubed into moles per dm cubed, which we can easily do because we know the MR of K, because we're told the M over Z for the molecular ion peak, so we turn that into moles per dm cubed, and then we can just use the relative sizes of the peaks to scale that up to get the concentration of M. That's the thinking. So the way into that, I think the first thing was that you really need to know that the areas of the peaks in gas chromatography are proportional to the concentration in moles per dm cubed. That's something you need to be aware of. But the other thing is, as we've said loads and loads of times right from the beginning of the course, whenever you see grams you should think like that should probably be in moles to let us do chemistry calculations, and the same applies here. As soon as you see grams per dm cubed you think, right, let's turn that into moles per dm cubed. So we do that first. So we get concentration of K in moles per dm cubed is equal to 9.13 times 10 to the minus 2 grams per dm cubed is the concentration divided by the molar mass, which is 166 grams per mole. You don't really need to put the units in, but it just helps to make sense of why we're doing that division. And make sure you're clear that we know 166 because that's the M over Z for the molecular ion peak, and that equals the MR. So we can plug those numbers in, and that comes to 5.50 times 10 to the minus 4 moles per dm cubed. Okay, and that's the concentration of K. So then we look at the gas chromatograph and we can see that if the area of K is 4.3, the area of M is 5.9. So therefore the concentration of M, we just scale it up. So we say it's 5.50 times 10 to the minus 4 times the area of M divided by the area of K. So it's that usual scaling thing that if this is bigger, it's bigger by a factor of 5.9 over 4.3, so the concentration is bigger by the same factor. So we just do that calculation, and that comes to 7.55 times 10 to the minus 4 moles per dm cubed. But if you write that down as your answer, you will lose a mark because the question specifies two significant figures. So you've got to make sure that you stick to that, and therefore the answer, actually, because it came out to slightly less than 7.55, it was just 7.5 times 10 to the minus 4 moles per dm cubed. Now for part 2 we have to suggest structures for these esters, and it tells us that this R group, which is, as you can see, part of the ester, is an alkyl group, so that means that whatever we come up with, it has to just be a saturated hydrocarbon group. So it was important to notice that in the question, because there were other possibilities if you didn't notice that, but they wouldn't give you the mark for those. So the thing to do is to work out what this bit adds up to, okay, without the R attached. And so you can do that just by counting the atoms. As always, be careful to count the hydrogens. Remember, you don't see them in the skeletal formula, but of course they're there. So you get the MR for that adds up to 137 if you add that up correctly. And that means for J that the R group has an MR equal to the total MR, 152, minus 137, which is 15. So that means that R has an MR of 15, and of course that equates to a methyl group. CH3 adds up to 15. So R is CH3, but you have to draw out the whole thing. This was a slightly annoying thing about this question, but you know, just do what it tells you to. So you draw the whole structure out, and then it's just got the methyl group stuck on there. Okay, so we can then do the same thing for L and M. So we can say, right, L and M, that R has an MR of 152, sorry, not 150, 180 this time, 180 minus 137, which is 43. Now 43, as an alkyl group, equates to 3 carbons and 7 hydrogens. Okay, 4 carbons would be too much, because that would come to 48. 2 carbons would be 24, but that would leave you with far too many hydrogens. So that implies that R is C3H7. Now the point about that is that that doesn't tell you what the structure is, because C3H7 is ambiguous. It could either be a straight chain or it could be branched. So the reason there are 2 of them is that one is the straight chain one is the branched one. Now if you just draw the structure up, so let's say, so this was J, so if we just say if you drew K like this, if you were to draw that, you wouldn't even get one of the marks for, sorry, this is L, isn't it? You wouldn't even get one of the marks for L and M, because they would say, well, you haven't shown me what the structure is. Because C3H7 is ambiguous, it doesn't show you what the structure is, and so you would get no mark for that. So you have to actually draw it out properly. So the quickest way is with the skeletal formula and say, right, well, it could get just a straight chain of 3, so that gives you 1, 2, 3, and that would be fine. And then M is going to be the same root of the molecule, but now connecting into the middle carbon to give you a branched one, so it's going to look like that. Okay, and that's M. Okay, so that was fairly straightforward, but there was this trouble that if you just wrote C3H7 there, you wouldn't get either of the marks for those 2, because it doesn't show you the structure.